Hello everyone, and this is Dr. Sivan Singh, and as we are already dealing with some reagents, we have already discussed 9 reagents in this row, and today we are going to discuss another important reagent, which is osmium tetroxide. And although this osmium, particularly this element, is very toxic element, but because of the usefulness of this osmium, we are using this kind of complexes for some particular purpose in organic chemistry. So today we are going to discuss about this particular osmium tetroxide, how we can prepare, what are the chemical properties which are associated with osmium tetroxide. We are going to discuss one by one. So before we begin, I would like to give a brief introduction of osmium tetroxide, that it forms basically monoclinic crystal. So we know already that there are 7 types of crystal system, and out of these 7 types, osmium tetroxide form monoclinic crystal. And if you want to know the parameters for monoclinic, then here are the parameters which is mentioned here. And then bond length, you can see none of them are equal, and alpha and gamma interfacial angles are 90 degree, and beta is not 90 degree. So these are the parameters for monoclinic crystals. If you want to study more, then you can follow any textbook. All right. So this was the first property of osmium tetroxide, that it forms monoclinic crystals, and this has a characteristic order it possesses, and because of this order, the name osmium is arises. Because if you see the general terminology osmium, which is given for this element, which is arises from the Greek word osme, which means order, and that's why it is called osmium. All right. So if you see the general appearance or general physical property of this osmium tetroxide, then generally it is colorless. But most of the sample which we see is yellow in appearance because of the impurities of osmium dioxide, which has this characteristics yellow color. So this also we have to keep in mind once we are dealing with this osmium tetroxide. All right. Another important feature of this osmium tetroxide is that it is volatile in nature. It's sublime at room temperature. So this is a very important physical property that we have to remember whenever we are thinking about this osmium tetroxide. And of course, as we have mentioned, that it is highly toxic, and still we are using this kind of compounds for some synthetic modification because of this special characteristics of this kind of complexes. So that we have to remember, and that's why we are using this. All right. So already we have discussed some of the physical properties of this osmium tetroxide, and one of the property is that it is soluble in buoyant range of organic solvents. So that is also you have to remember. The solubility in water is very low, very low, and then it is tetrahedral, and therefore it is non-polar species. So we know these things. All right. One important feature is that it is one of the densest element in the periodic table, having 22.59 gram per centimeter cube density. So this is quite high. Melting point is 40 degrees centigrade. Boiling point is 130 degrees centigrade. So these are the some physical properties of osmium tetroxide we have to remember. Okay. So as long as you see the preparation part of this osmium tetroxide, then we can easily prepare this osmium tetroxide. Once we are treating this osmium, powder osmium with oxygen at room temperature, we can prepare. But if we are taking solid osmium, then we have to heat this compound up to high means 40 degrees centigrade, 400 degrees centigrade, then we can have this complex. So this is quite easy to understand. And the most common application or most important thing which is associated with the property of osmium tetroxide is that it is used for the dihydroxylation of alkene. So this is the most important property which we have to remember. The second thing in this direction we have to remember is that it always give 1,2-diol in vicinal fashion. Stereochemistry is always same. So these are the something which we have to remember. So this is the summary part. Once anyone is dealing with osmium tetroxide, so this is the summary which you have to always remember. So this is the most useful part in my opinion. Of course, there are several chemical reactions which are given by osmium tetroxide, and we are going to deal one by one. All right. So if we talk about the application part of this osmium tetroxide, then fundamentally it has four major application. The first one, as I have mentioned in the previous slide, is the dihydroxylation of alkene in the cis fashion. So this is the first one. And the second one is if you want to prepare some enantiomerically enriched compound, then we are using some asymmetric fashion. There are some asymmetric chiral ligands which do hydroxylation in the alkenes particularly. So we can prepare chiral alkenes, chiral diol compound used from alkene using this reagent. We'll talk about this asymmetric hydroxylation reaction. Then we have Lemieux-Johnson oxidation reaction. Here, cleavage of double bond takes place, and with the help of oxidizing reagent, which is sodium periodate in this case, it cleaves this dihydroxylation carbon-carbon bond. This carbon-carbon bond is cleared by this sodium periodate. So we'll talk about this also. So then we have a reaction with alkyne. So once we are treating with alkyne, then we have some product which is formed. Of course, it is a 1,2-diketo type of product which is given out as a reaction of alkyne with osmium tetroxide. We'll talk about it. So these are the four major applications which we have to remember whenever we are thinking about this osmium tetroxide. So coming to the first one, which is called dihydroxylation of alkene. So if it is, simple alkene, and we already know that osmium tetroxide is basically a compound having +8 oxidation state. Osmium is there in +8 oxidation state. And once we treat this osmium tetroxide with any alkene, then the reaction takes place in cycloaddition fashion. So 3+2 cycloaddition reaction takes place between this osmium tetroxide and this alkene to give rise this osmate ester intermediate. So this is called osmate ester. And now you can see that the osmium is converted from +8 oxidation to +6 oxidation state. And after this hydrolysis, this bond getting cleaves, and we are getting this dihydroxylation of alkenes as a major product. And of course we have this side product. So this is the first application of osmium tetroxide which we have to remember, and that is called dihydroxylation of alkene. One of the most useful reaction of osmium tetroxide once we are treating this osmium tetroxide with the alkene. All right. So here are some of the example. You can see here, this is the alkene bond and this is dihydroxylation. It can be seen here easily. Here we have alkene, double bond. Of course, these are the aromatic pi bonds, so it will not be cleaved. The bond is very stable. We know all these things, so this bond will not be reacted. This bond will not be affected, and this bond will give rise to this kind of dihydroxylated compound. Similarly, we can have this kind of complexes. You can easily see dihydroxylation. So once we are using this pyridine, then the rate of reaction is faster. You can see within 30 minutes we are getting this product, but once we are using simple reaction, then we are getting almost 24 hours. So the rate of reaction can be enhanced in the presence of pyridine. That's what I want to mention here. So one more thing which I would like to mention here is that we can regenerate our osmium catalyst, because we know that once we are treating osmium tetroxide with some alkene, then this osmium +8 is getting converted into +6 oxidation state, and therefore if we are using some oxidizing reagent such as tertiary butyl hydroperoxide and methyl morpholine N-oxide, which is called NMO, molecular oxygen, sodium periodate. So these are some reagents which convert this reduced osmium 6 into osmium 8 stage. So once we are adding this kind of oxidizing agent, then it will regenerate the catalyst so that we can have high yield of product. We don't have to add huge amount of this osmium tetroxide, because once we are adding some oxidizing agent, then it will be catalytic and we can have a variety of product. Means the turnover number of catalysts can be increased, so we can have a high amount of dihydroxylated compound. So here also you can see dihydroxylation happens in the presence of this kind of oxidizing reagent. All right. So here are some other examples. You can see here some oxidizing agent, then dihydroxylation. This is the alkene. and these are the some oxidized product, means the dihydroxylation product. So we have a variety of application. You can go through one by one. So you can see there are a huge variety of application of this, osmium tetroxide. We are using some oxidizing agent, and then we are having this dihydroxylation species. All right. Now, if you see the oxidation of alkene with the presence of osmium tetroxide, then the first one is of course, which is called John dihydroxylation reaction, which is catalytic oxidation of alkene in the presence of some oxidizing agent. And then the second category is called Sharpless asymmetric oxidation, Sharpless asymmetric dihydroxylation reaction, which is basically discovered by scientist Sharpless, and because of he has given tremendous time for the discovery, for the research, for the development of chiral dihydroxylation of alkene. So on his honor, we are calling this as Sharpless dihydroxylation reaction. All right. So what happens in upjohn dihydroxylation is that we are using this osmium tetroxide, 1% you see, a huge, very less amount of osmium tetroxide, but we are using this N-methyl morpholine N oxide, NMO, as a, oxidant. So it regenerates this osmium species, osmium plus 8 species, and we are getting a high yield of dihydroxylation compound. But if you see that surplus dihydroxylation reaction, then we are using this mixture of, reagent. You can see here we are using K2OSO2 OH4, K2CO3, and this is K3FeCl6. In addition to these reagents, we are using DHQD, dihydroquinidine fall, and then we are using dihydroquinine fall. So these are fall stand for this is a here. You see, this is called thalazine, and if you see the all the structure, the chemical structure of these two reagents, which is called DHQD. This is called DHQD quinine, and this is called DHQ quinine. So these are the structures of the catalyst. Technically, it is called AD mix alpha. It is if it is DHQ pul. If it is DHQD, it is called AD mix beta. So these are the two commercially available catalysts that can be available in the market, and we can prepare this kind of chiral compound in the presence of any alkene. Is once we are treating this kind of alkene with these complexes ADMX alpha and ADMX beta. So this is what I want to share from here. So we are using chiral ligand, and we are having these chiral compounds. All right. So what is the basic role of these chiral ligands? If you want to know the basic role, then we have to go through again, general reaction of alkene with osmium tetroxide, and we know once we are treating alkene with this osmium tetroxide, we are getting this diol. But the stereochemistry of this diol is not defined. One can have mixture of product, recipe mixture we can have. But once we are treating this optically active ligand, then we will get specific stereochemistry of the product. If you are using beta, then we will get the dihydroxylation on the top of the face. If you are using alpha, then we are getting dihydroxylation bottom of the face of this alkene mode. And that is the role of this catalyst. If you are using beta, then it will attack the OH species, will attack from the top of the face, above the face. This is called beta attack. All right. If you are using this catalyst, Admix alpha, DHQ full, then the attack takes place from the bottom side. So this we can easily understand. These are the role of this catalyst. So actually the mechanism of this reaction is very complex. I don't want to show the mechanism here, but in this particular lesson, what I want to show is that how we can generate chiral hydroxylation species from alkene using this asymmetric dihydroxylation, Sharpless asymmetric dihydroxylation reaction. So we have a variety of examples. We can see here, if you are using alpha, then this is bottom face. If you are using beta, then this is the top of the face. Then we are using beta, means we the hydroxylation from the top of the face. So these are some examples which we should remember. Anyway, So these are some points which we can easily understand. Already we have discussed, so I don't want to read those topics, those points. The third application of this osmium tetroxide, which is called Limiax-Johnson oxidation reaction. And here we are converting this alkene into cis diol in the first step, and then once we are using this sodium periodate, this sodium periodate to oxidative cleavage of this bond, and we are getting two aldehydes. Two carbon compounds are generated because of the oxidative cleavage of this carbon-carbon bond. So this particular application is called Limiax-Johnson oxidation reaction, very well known in organic chemistry. So these are the examples we can see here. We have this alkene. Once we are using this sodium periodate, then this bond will be cleaved. First, it will dihydroxylation will take place, and then it will be opened. So this aldehyde will be generated. Once we have this double bond here, then this will be hydroxylated first, and then this keto group will be generated here. So this is the application osmium tetroxide. Once we are using some alkene with sodium, so with the osmium tetroxide in the presence of sodium periodate, we are getting common compounds. So the mechanism you want to see, then the mechanism is very easy, and we know that the first step is of course 3+2 cycloaddition reaction. We are getting this osmotic ester. Already we have discussed. But since now we are using sodium periodate, then this sodium periodate will oxidize this osmium species to +8 oxidation state. So this is important. This step is very, very important. And now we know that we have this IO3 minus in the solution, and this IO3 will react with this osmium species, and it will generate this intermediate. And once this intermediate is formed, then it will rearrange in this fashion. You can see here bond is migrated in this order. This bond will append, and this will give rise to osmium tetroxide will be eliminated, IO3 minus will be eliminated, and then we have this cleaved carbon-carbon bond having carbon, RCHO, R1CHO, R2CHO. So two carbon group is regenerated. So that is important. So we have to remember that once we are treating this osmium tetroxide with alkene in the presence of the sodium periodate, this oxidative cleavage takes place, oxidative cleavage of this carbon-carbon takes place, and we are getting common compounds. All right. So the fourth and last application, which is useful in organic chemistry, which is associated with this osmium tetroxide reagent, is that the reaction with alkyne. So once we are treating alkyne with osmium tetroxide in the presence of tertiary amine, such as pyridine, to give osmium ester complexes. This is important. This is extremely important because this is an intermediate which is formed once we are treating this alkyne with this osmium tetroxide, and it will further hydrolyze to give corresponding carbon compound. So here you can see if we have this alkyne, and then we are getting 1,2 dicarbon compound. Here this is alkyne, then we are getting 1,2 dicarbon compound. So this is terminal alkyne, and in this case we are getting carboxylic acid. Of course, one will be carbonyl, one will be the carboxylic acid. If you want to understand the mechanism of this reaction, then the mechanism is very, unique, very, complicated. Intermediate is formed here, because once we are treating this alkyne with osmium tetroxide in the presence of pyridine, so this kind of intermediate, because it has two pi bond, so one intermediate, one osmium ester is formed in this side, and second is formed in this side. So that could be easily seen. And once it is formed, then the bond will cleave in the presence of sodium sodium sulfide in this fashion. Like suppose this bond is cleave here, so this carbonyl group will be regenerated, but this bond will open. So this bond will be here, and then this bond will move. So you can see here these two carbonyl, one carbonyl is retained here and one carbonyl is retained here, the rest is cleaved. So we are getting this 1,2 dicarbon compound. So this is it from the osmium tetroxide part, and we know the general features of this osmium tetroxide. Like this is volatile compound, it sublimes, and there is unique property having very specific order of this compound, and because of that order we are telling this compound as osmium, because it is arising from the Greek word osme. Then we can prepare this osmium tetroxide, because once we are treating this osmium in the presence of oxygen, then we can have this compound. So preparation part is very easy. As far as the application is concerned, then there are basically four main applications which are directly related with this reagent. The first one is extremely important, that is dihydroxylation of alkene. So once we are treating any alkene in the presence of osmium tetroxide, then osmate ester will be formed through 3+2 saccharide reaction, and it will give rise to dihydroxylation compound after the hydrolysis. Then the second one is the Lewis-Johnson oxidation. Once we are treating this reagent in the presence of sodium periodate, then the oxidative cleavage of carbon-carbon bond takes place and respective carbon compound is regenerated. And the third one was surplus osmotic dihydroxylation. And we know that once we are treating this kind of alkene in the presence of this AD mix alpha and AD mix beta, then we can have stereochemistry bottom of the phase or above the phase of above the plane of the alkene can be generated. So that's what we already studied. Then the last part was the reaction with alkyne. So once we are treating alkyne with osmium tetroxide in the presence of pyridine, then we are having 1,2-dicarbonyl compound, and if it is terminal alkyne, then we are getting carboxylic acid at the final product. So these are the some important features. I hope the lesson will help you to know about the general features, properties, and preparation and application of osmium tetroxide. And next we will discuss perbenzoic acid, which is also an useful reagent. And we'll talk about this reagent in the next lecture. Thanks for watching.